Thank you. I'm talking about approximation. Okay. In fact, I think everybody is doing approximation. I started doing approximation since I was a PhD student, and I'm still doing approximation. And there are all kinds of approximation. And deep learning, in many sense, is also doing the approximation. You have a data, which is the labeled data. Then you basically you can consider the labeled data is a sample of underlying function. And in most cases, you want to find the underlying function to generalization. So in fact, recently I realized all kinds of approximation, no matter which way you use, is always about composition. You're using the composition of the function to get your approximation. Okay, let's look at the outline. I will briefly introduce approximation. I know many of you already know, but I try to see how do I look at this approximation in the view of the composition of the function. And then how do we view the deep learning as a composition of the function to approximate another function. And then I started a little bit of approximation for the CNN, also sparse coding, Mickey's favorite. And for that classification case, how does it approximate? So finally, I want to back to this classical approximation, which I think in the feature space, you still using classical approximation. Okay, let's start with this brief approximation. What is the approximation? You have an f in your f you want to know. You may only have a data for that. You want to find a function g, which is simple. What do I mean simple? Simple, either you like the function, you think it's simple, or you may don't like that, but this function is easy to compute, or the function has a good analytical form for you to manipulate. So this is g. So you want to have what? Because you don't have a f, you want to use g to replace f. Of course, you want to g to close to f up to a certain error. Okay, in some norm, some distance. Okay. But sometimes your g can be simple, but g not necessarily need to define on the RD. You can define the Rn. That's in the deep learning case. Rn more like your future space. Your future space is different. But then if it's this case, and your g can be simple, it's linear, or you maybe use the fully connected net. That's basically piecewise linear. You can use the linear. This is a very simple function. Linear, piecewise linear. You want to the g is simple, but for this approximation to make sense, you must have a map. Okay, this map is t. T from Rd to Rn. Then you hope that you have a proper t. So f minus g composed with t smaller than epsilon. That is the approximation. Okay, if you look at the classical approximation, in the classical approximation, in fact, they never say in this sense, but they do in the same way. The only difference is the t they are given. Normally the t is given to you. Then once the t given to you, essentially they find a is good enough. Most of classical approximation deal with that. For the deep learning, your t is not given. You hope to learn this t or construct this t from the data given. Okay, for the classical approximation, the problem is that your t is independent data essentially. However, if you want to have a small epsilon, your n has to be big. And if your d is huge, your n can be much more huge. Okay, that's the. Okay, let's look at the simple case classification. Linear. If you look at the classical approximation, there are two. One called linear approximation, one called nonlinear approximation. Okay, linear approximation is older than nonlinear approximation, but compared with deep learning, it's still older. Deep learning is younger. Okay, so linear approximation is very simple. You choose a generator, normally the basis, or sometimes even also normal basis. Okay, generator, because this generator is a nice function. It's spline, wavelets, whatever, finite elements, and whatever. Okay, you like. Then your t is essentially this map. Very simple. This is a factor from Rd to Rn. This is the map. Then you basically your gx is a dot x. At the end, you just find a so that gt equal that you want to see so approximate f. That's the linear because why it's linear? Because you have a f1 g1 plus approximate f, g2 approximated f2. The sum have a good approximation for the sum of the function. Nonlinear, basically you have a much larger generator, can be infinity. But however, you want to what? You want to see t is a map from RD to R infinity of very high dimension. Then when you find the G, this sequence A only find support. Say only have n non-zero entry. Okay, that's the issue. That's become a nonlinear because your different function, your support of A can be different. So your sum will not lead to the sum of approximation. So that's why it's nonlinear. Let's look at little bit more detail, like a simplest case for the L2 case, Hilbert space case. It's easy because if you have 5G, you select first n term, this approximation is basically orthogonal projection. Okay, that's the best approximation you can have. Okay, this approximation is good when your sequence have a fast decay. Then when J go to infinity, your system will have a very good approximation. So if your sequence has a fast decay, that means your f, underlying for f, has to have some regularity or smoothness. That's what you should have. Otherwise, you don't have a good approximation. Okay, so that's why linear approximation provide good approximation for normally a smooth function. And of course, when n go to infinity, you reproduce every function. That's essentially what so-called Hilbert reproducing kernel space. You basically pick n equal to infinity. Okay, so the advantage is that when D is small, domain is simple, function is smooth, you do have a good approximation. Okay, that's why finite elements, spline, all this works for so many years. And disadvantage, of course, one of them is a curse of dimensionality. So for nonlinear approximation for C case, also simple. If you have this orthonormal basis now, you just you make all the inner product, you order that, take a first n leading term. That's the best nonlinear approximation for n term, for any f. Okay? So of course different f, your term is different, your index is different. So that's what is nonlinear. You can see for nonlinear function, a nonlinear approximation, your decay of the sequence is demand for that is not as that much as a linear approximation. That's why nonlinear approximation can use to approximate piecewise smooth function. That's why wavelet works. Okay. So nonlinear approximation is better than linear approximation when f is non-smooth. Okay. But still you have a curse for dimensionality. Okay, to summarize, both linear and nonlinear approximation are scheme basically to me is like since your t is fixed and the approximation is for classical function. In some sense, this is more like a change basis. Okay? And this linear approximation is not good when your domain is very complex. Okay? Your function form can be complex, but domain normally is simple. Okay, even you do the finite elements, you think the domain is complex. Compare what you deal with deep learning, the domain is much simpler. Domain is simple. However, the deep learning, T is constructed by given data that adapt to the underlying function to approximate. The T is not say fixed for a classical function. Each f, different f, we have a different T. It's a T is constructed by data. To me, it's more like a change variable instead of change basis. It's change variable. The change variable for what? Change variable try to map your domain to a simple and better domain. It's most of the time is a feature space. Feature space so that you can have a good approximation by classical approximation. So that's okay. So now you think if you agree that all the approximation is about the composition of functions. Now we have to ask the first question. Okay, before I answer the setting. Okay, this is your given data. If you are in the deep learning, this is your label. Okay, xi, fxi label. So your key is deep learning is construct T. So that T have a T kind of simplified domain through a change variable, and T maps key feature of f and the domain of f, so that it is easy to find G such that G composed with T give approximation. Okay, we can see if all kind of learning scheme is basically doing this kind of thing. Now how to construct the key issue is how to construct map T from Rd to Rn such that a simple function for a simple function, for example, linear function, from data such that G and composed T can have a good approximation for f. That's all the learning procedure is doing. You find the T, how to do that. Okay, do nicely. Okay, first question. Okay, here I'm missing N. Okay, first for given f and G, can you always have a T mathematically? Can you always have a T for epsilon for given f and G and epsilon? Can we all have a T Rd to Rn such that this can happen? This is the first question you have to ask mathematically. Answer is yes. In fact, the condition is very simple. Proof is not so complicated for this one. You have f is that, and G is given as long as your range, essential range, I will say essential range, that is for G is contain f. Then for actual epsilon, you always can find T such that this happen. So the actual your G always can approximate f within epsilon as long as you have a T. There exists T. We can prove. Even we can write the T. If you have f, I can write T out exactly. What is the T you should keep for the given epsilon? It depends on epsilon, but you can write out. Okay. But it's a write out. You can able to write out when your f is given. That doesn't mean T is easy to learn. Of course, T is easy to learn if f equal to G. Okay, T equal to identity, right? Yeah.
What's the regularity of f and G?
You don't need regularity.
C1?
No, don't need. No. It's because it's not we are not talking about the approximation order yet. We talk about the density. Yeah. This is okay, that's the key. If you use the classical approximation, your n must be good. Here, n can be any number you like. Okay, it can be bigger, can be small, can be 1. Of course, it cannot be 0. Okay. So, first question is good, mathematically good. But second question, okay, T is so complex. Can I decompose T to a composition of a simple function, simple map? That's another question. Second question, if T could be a composition of a simple map, that you can have a T equal T1 and Tj. And each of them is simple. Okay, what do you mean simple, you will ask? Okay, for example, I said T is perturbation of identity. I think it's simple. Okay, we have a next theorem. Say, if you have a f from Rd to R, G, that's the condition is same. For any of the, then there exists the J. Okay, I don't have an estimate of J. I don't know how many J, because it depends how simple you are. Okay, such that this can happen. Okay, in our paper, we can write Ti exactly what a Ti is, each Ti, Tj is. It's very simple, but unfortunately, we don't know exactly what a J is. We know there exists J. Okay, you cannot say given this f and g, I have a J equal to 100. I cannot say that. Okay, but if you think about deep learning, each one is a layer. So this is the layer, basically. Okay, if you are mathematician, I think you finish. Okay, that's all. You have this one, you have that. But people are not happy. People say, no. This is T. How do I? I can write because I can write in a A. Okay, in the term of the F and term of your T. So next question: can I mathematically construct it step by step for the Ti? Okay, first of all, if you gave me full F, I say yes. I can have a constructive way, computable way. Not just theoretically say I exist, I can exist form. I can computable way to do that. Okay, this proof is constructive. That means I say, okay, first you do this step, you get this T1, you go to that. Okay, that's the computer. Okay, this if you are applied mathematician, you are happy with that. This is finished. Okay, your theorem is complete. But if you are computational mathematician, if you are computer scientist, you are not happy because I don't have an F. I only have a what? I only have a sample of F. So following question is that, given a sample, can you design a neural, deep neural, to do that? Yes. We design a neural according to our theory, according to our method, such that F compose, you can learn this T tilde, G tilde by minimizing this one. This is a deep learning scheme, such that this can smaller than epsilon. The neural is different. Architecture is different. But there is architecture, and we do some primarily numerical simulation is promising. Okay, we are still doing that. If we finish that, we will finish the paper. So we will wrap up the paper and finish it. Okay, we are doing that. We want to have a more example to show that. Okay, we do design architecture. It's a deep learning kind of architecture. With this minimization, you get this one. Okay, so there are many ideas for this paper. I don't want to reveal every ideas because I have not finished the paper yet. But I can give one simple idea. The simple idea is that's simple everybody have. Basically, essentially, this one is you learn. Okay, you learn. You want to approximate F you don't know. You only have a label or your sample of F. Okay, that's what you have. Okay, you want to do that. What I do? This one is theoretically you cannot have. This one you know by mathematical analysis can approximate F. Then I estimate this one, how this one approximates this one. If this have a good approximation, that's have because your data is randomly given, so if you have a probability, you have a high probability that's close to that. Okay, so this is called C part normally called bias, C part is variance. Okay, look at the statistician. Normally they assume this part, and like a kernel method, they assume this part. Most of estimate is this part. But for deep learning, for CNN, for many other, this part is hard. This part is because of many tools available. This part, almost no tool. Okay, that's why we need a mathematician. Okay, looks exciting. I still have lots of time. I've already finished almost all my talk. So the theory is complete, looks like, but does not answer the question, all the questions. For example, I don't have, say, if you ask me, okay, now you have this beautiful theory. If I gave you, okay, can you estimate your error in terms of knots? Okay, so that's if you haven't do that, that's basically like you have an approximation order kind of things. Then if you want to do that, I'm sure you need a regularity of function and many property, but we don't have. Okay, we don't have that yet. Okay, and we are going to find, okay, maybe 2 years ago, I don't have a previous theory either. Nobody have that theory, but maybe after another 2 years, we will have that. That's I think, I'm sure somebody asks regularity or smoothness. You want to do that, your smoothness of function will come in. Otherwise, I don't think you can do that. Even with that, at the system mode, I still have no idea. Okay, then another problem. There are already many available architecture of machine learning or deep learning. They are not our architecture. So those architecture, do they still have approximation? Can we build some theory or some kind of estimate for those architecture? Okay, I will give 2 examples. One is CNN, one is sparse coding. Okay, and also not for arbitrary F, only for classification. Okay. Yes, there are some progress. That's so like a classification. Okay, how many class is not important. So we make life simple. Say you only have 2 classes. Okay, you have 2 class. You have omega is omega 0, unit omega 1. They have to disjoin. If they are not disjoined, you have no way to separate them. Okay, their closure should be disjoined. Then your underlying not your label. Your underlying function basically is very simple in terms of the value of range. You want to say what? Omega x in omega 0 equal to 0, and x in omega 1 equal to 1. That's all your label satisfies this. Okay, but you only have a label. You want to find fx. This kind of function we have is the function has a very simple form, but the domain is extremely difficult. Yeah, extremely complex. That's different from a traditional approximation theory and this deep learning case. Your function form is simple, piecewise linear or piecewise constant. But your domain is so complex. You have a kind of handle because most time you have an image, like image classification. Your domain is what? Is in the failure 256 by 256 dimension. This is maybe in the high dimension space, lower dimension manifold, omega 0 and omega 1. So domain is so complex. Okay, so that's why you want to construct T. T is the map. Essentially what you do, your T maps this omega to a simple domain. You call feature domain. The feature domain, you hope what? The feature domain, the T is the magic. Magic say remove all the nonsense. That's not affect your classification. You just take them, try to remove them. So they keep the key things. That's what you want to. That's essentially. So essentially you have this so-called image space. You use T map to feature space. After that, this is nice. So what? In the like CNN, you use the fully connected, to me fully connected layer, and to get a function. That's basically, it's here. The space is so simple. You are able to use the piecewise linear function spline to approximate. Okay. In some case, you just use the linear function. In some classifier, you just use linear function. For this case, you use piecewise linear. So essentially, here you want to directly use the piecewise linear. You can use the fully connected. You can have, but it's very hard for you to do that. That's exactly what it is. Okay. So G can be like a CNN. You basically the fully connected plus soft max. They construct a feature map T so that G composed with T approximate F. Where? Okay. Because when people when we see the paper were written and signed, of course, sent to the journal and rejected. Because we already have an approximation for fully connected net. Why you need that? But the issue is that the fully connected is not linked to the image domain. Your image domain you don't have. You are in the feature domain. Your approximation want to approximate function from image domain. But the referee does not get it. Okay. So we revise the paper. From C conference, I learned a very good factor. Every good paper has to be rejected once, at least. Okay. Now, the key, key, what is the key to T? T, you don't need to have a good approximation. What is T? T, you have to what? Have two properties. For this classification, okay, only for this classification, not for other. First of all, you have some kind of smoothness in the, because this basically is what? Called Lipschitz. Okay, this way, basically you want to, when the 2 points in the same class after your map, you don't want to go too far away. All right, this is basically. But this is the key feature for classification. The second property is more important and hard to keep. You want to what? You want to when the 2 points in the different class, you don't want to then merge to the distant 0, merge to the same class. So you want to them keep away. In fact, if your 2 set is like that, it's harder for you to do the classification. You want to push them out like that. That's easy. Your one line can push them. That's what it is. You want to have this property. That's what you keep. So, but this property for the given CNN, it's not easy to prove. For given architecture, because not designed by me, it's designed by somebody else already there. You want to, given this architecture, you want to do that. It's not easy. But that's what we did. We try to prove have this property. Then you after everything, you have an approximation. Okay. Okay, this I think I skip this is basically a notation for CNN. You have a G, this is a CNN, and okay, of course, if you let your filter long enough, as long as the image, you don't need to do anything. It's one layer. It's fully connected, but you cannot do that. Your CNN, my understanding is your each filter should be short. Okay, you cannot if you allow to long filter, it's you basically like a fully connected net. Okay, so what are the results? Okay, CNN we know that all the numerical results tell you that you after you train your CNN net nicely, all the results tell you your CNN achieve desired classification accuracy with high probability. You cannot say for sure. Okay, most likely it's very true. Everybody sure I have 80%, 90%, 99%. It's probability. Right? But do we have a mathematical proof for this statement? I don't see anything yet. Okay? So what we prove is that we can prove that for any given epsilon, and this accuracy close to 1 up to epsilon have a high probability. Probability also close to 1. That's the theorem. Okay. The key issue is still to prove the T-tutor you learn from CNN, from image space to the feature space, satisfies the two property. That's the key. But this is still the key for that. This paper is rejected. Okay.
This is for the test data?
Huh?
This is for the test
No, for general, of course.
Training?
For training. For test, no meaning. It's for the training. Of course, you have, test data is a sample you gave. Then you get fx. X is for any x. Of course, for training.
So I didn't understand your answer. This is for the test data eventually.
Not for test data. No.
This is only for the training.
For everybody, not only for training. For everybody, not for training. For the any image. Everybody else understand.
Can you go back?
No. Everybody else understand. Let me talk to you after that. Anybody else has a problem for that? Your training fx, your x for any x. Your training set is just xi, right? That's okay. I look at my time. See whether I can entertain you. No, I don't have time. Okay. Next is your favorite. Okay, sparse coding. Okay, this is sparse coding. This you should not have a question. Okay, this is the minimization. Then you try to training the dictionary, and of course this C is your this coefficient. Okay, this is a main algorithm, and we also develop an algorithm. Okay, our algorithm for this model we have a convergence analysis. We do prove it's converged. Okay, other algorithm may not converge. I'm not a complainer. I just say fact. Okay, this is what we do. But still, this one you have nobody. I don't see. Maybe Mikino. Nobody prove the accuracy analysis as I did before. Okay. Now whether this one have, I don't know. But I have another model. I instead for L0 norm there, I change L1, and I using this fully connected net. Okay. I use fully connected instead of there people using linear, but here you fully connect. Okay, I have this one, and first I want to say if you change to this model, your numerical results does not affect too much. Okay, still have a same. This is this model compared with other, not much different. Okay, that's okay. But here for this one, we do have a mathematical analysis for the accuracy. Okay. So this basically this is your T. Even you have a trained dictionary. That's the encoding. Using encoding, you can get you have a G and a component T. Then you have the same accuracy analysis. Okay, not for test data. Okay. Okay, so for any x you put in, you have this property. Okay, your accuracy, that means your accuracy close to 1 has a high probability. Your accuracy close to 1. That's okay. Forget about your own notation. You have a high probability your accuracy close to 1. Okay, this one you will like it. Okay, this one is a little bit off that, but connect to what Mickey's last talk for the they call convolutional sparse coding. Okay, few years ago, I'm a wavelet guy. Okay, I'm doing wavelets, and I using wavelets together with Stan. We did lots of image. Okay, with Stan TV, we make the connection, and we do lots of imaging things. Then one day, okay, all those methods, it's true, based on sparsity of the either wavelet or TV. Basically, your function, your underlying function on the wavelet transform or TV transform, you have a sparsity. All those things work because of that. So that time, because we worked so many years, I naively enough think about, okay, since the quality of your perform of your algorithm depends on how sparse you can approximate on the how sparse approximation is, how good the sparse approximation is. You see, you make a record, make me nervous. Okay, how good the sparse approximation is. The quality of a sparse approximation depends on your quality of the performance of your algorithm. So because of that, we decided to, okay, how about I learn a tight wavelet frame according to your image you gave to me, not from the whole set of the image you gave to me. Can I learn a tight wavelet frame? Under that tight wavelet frame, my image have very sparse, good approximation. That's the idea. Okay, so that's why we started system model. System model is that Mickey doesn't like, but I like it. Okay, this we minimize. Okay, normal model is just without W. We minimize C and W such that this happen, and this because we have a tight frame is this one. But if you know wavelets, see W is not just actually W. This is a huge matrix. W is a convolution matrix. That means it's a wavelets. You basically have a filter. Once you have a filter, you can design the decomposition algorithm. That's all. So see W like a tall and fit guy, tall and thin, very tall. How tall it is depends how many filters you use. Okay. Then the low is like a low. If you depend on what kind of boundary condition you use. If you're using periodic boundary condition like a circulator matrix, block circulator matrix, more or less like that. Okay. Then this W we call decomposition matrix. That's your lows are your system. The lows will form a tight frame. Okay. Lows we talk because it's a rectangular matrix. Your column is much bigger, but the column is also normal if it's a tight frame. But lows not. Lows are redundant. It's a highly redundant system. Okay, that's what it is. But this is the minimization problem. It's hard, but this is what? This if W only if W is tight frame. Okay, Mickey like a frame, but I like tight frame. Tight frame is a special case, special set of frame. Okay. This tight frame is this one. You have this property. If a tight frame, this minimization is equivalent to the this minimization. Okay, this is data. This is your C. Try to find this. This is essentially what? If you Stan will know. We are happy to see. This essentially says you have a data. You make a transform. This tight frame transform. Do the hard threshold. Okay. This is good, but be careful. This is only equivalent. This one doing that is exactly minimize this one. It's not your synthesis model. Okay. Okay. Then, if you say okay, I forget about the W is a tight frame. I just arbitrary frame more general. Okay, you still can do this one. Of course you can. But this one here, this term will be much more complicated. You never get a synthesis model in any case. Okay, if you do that, you don't get a synthesis model. Okay, synthesis model you cannot get it this way. Okay, unless W is orthonormal basis instead of tight frame. That means no redundancy. No redundancy, your WWT become identity. So these terms automatically drop. Otherwise you cannot. Okay, so that's the key. So why I like tight frame? First of all, for encoding. Encoding, once you change the encoding is just simple, very simple. You change to the whatever domain, you give it to the coding or operator, then do the thresholding. If you do use the other frame, your encoding is much harder. You want to have an image domain, you have a good minimization. Okay. Second, decoding. your decoding, your tight frame is very simple. Tight frame decoding and encoding is almost the same. The reconstruction is also just a WT is also another convolution. But if you are frame, you have to have find a dual frame. Dual frame normally have a longer filter. That's not a problem. If your condition number is not good, your any perturbation here, you blow up error. That's why I like tight frame for this. We didn't call that. I borrow your name. For this one, we're using tight frame instead of frame. Of course, people will complain and say that if you use a tight frame, you have a constraint. This constraint it becomes constraint optimization. Because if you use frame, you can drop this one. But very strange and very luckily for this case, this condition help you. Why? Because how do I solve this minimization problem? I solve this minimization, this is the same. This is equivalent. Alternating. Of course, you fix W, find C, it's very simple. One hard threshold. Get it? When you fix C, find W, if you want to frame, you go, you work hard, it's hard to find. Fortunately for this one, because of this property, you can write down analytic form and in a small matrix, not a huge matrix. Each block, you have your filter. Your length for filter and the number of filters, this is the block for your matrix. Your block for matrix, you can write down exact analytic form for those blocks, then you can generate W. So both step is one step. Both sub-minima optimization problem is a one-step solution. You don't need to iterate. So this algorithm is very fast. Now, of course, next question you will ask, okay, I iterate because I fix C, got W, fix W, get C. Do I converge? Yes. We do have a theory. It does converge. Converge is stationary point. Yeah, but in some case, it's minimizer. Okay, we have a condition on that. Station point not just says this cost function value go to 0. This station point is almost like a minimizer. You look at our definition for station point. It's some direction minimizer, more or less like that. You can check the detail in the paper. With our stationary point is a bit stronger than other. We're using the name called stationary point. So that's I think I will call I call wavelet tight frame, data-driven wavelet tight frame. Now Mickey call convolutional sparse coding. Okay, I think what the time? What is time? 5 minutes. Okay, 5 minutes is good enough. Fortunately, I did not answer your question. Okay, this one not important. Okay, these two papers important. Okay, this paper is good. Never rejected because Charles Chui. No, because Charles Chui know my research quality. He's the editor-in-chief. So he looked at the paper great. Both papers accepted. Okay, never rejected. Okay, maybe not good enough. Okay. Okay. Now back to the classical approximation. Okay. In fact, in the future space, you're still using classical approximation, as I say. Okay. So approximation in feature space. I think approximation in feature space so far we're using either linear or piecewise linear, but still you have many room. Okay, when you go down to feature space, maybe dimension is lower, or maybe the domain is better. Maybe you have a room to do something else. Okay, so that's why my point. Okay, that's why the classical approximation is still useful. Okay, not to say we can forget about the classical approximation, but I think it's in the feature space, not in the original domain. Okay. So this I think the deep learning, also the machine learning architecture help you simplify the domain, move this complex domain, very complex domain to a feature space. Okay, so but for this one, you still have an approximation problem. What's the approximation problem? So even for classical approximation, now you have a set the data. Data make noise because your okay, maybe notation. Okay, I should unify uniform notation. But anyway, your data here, maybe is a sample for F, you have a noise. Then this is your Y. You want to recover F. Here is still in the future. Okay, in the future space, but it's still you want to recover. This F is like my G. Okay, sorry about that. It's like my G. You want to recover that. So you want to, if you recover that, you have a noise. You have some way to remove noise. Okay, you have a TV mother, whatever. You can remove noise. You always when you remove noise, you have a data. Then you have a data. Then you have a no. This is my G now. You have some scheme to reconstruct from data reconstruct X or G. So fundamental question you still may want to ask. Okay, doesn't matter how do you get this way. You have all your favorite scheme to remove data or remove noise. Okay, so that doesn't matter. You map from original space to the future space. Your data still have noise, or still have all kind of errors. Okay, you have a magic way to get your yi star from yi. That's fine. Then you have a magic way to reconstruct your x function, reconstruct function g from that. Doesn't matter what you do. Okay, using whatever your favorite method. The fundamental question is that when my data go to dense and dense, whether your g will go to f. That's still the question. Okay, and I think this is only, or not only for this case, only also for all the other denoising scheme. You also can consider this matter. Okay, this I format in a feature space, but in the other domain is the same. Okay, what do you have? Okay, I think I don't have time. I don't go to detail, and you can ask whether your G converge to F, and you can ask what's the rate, and what's the noise level, how to relate to noise level, and can we have G go to F? That's the question you want to ask. I think I've omitted all that. I have a result. Result is when I use the wavered method to the construction, I have this one. My G in my construction. Okay, you can look at these papers are available anyway. Also did not reject or not reject. Okay, minus F have this error estimate. Okay, you are with the confidence data. Okay, that means probability is 1 minus data. Okay, if your data is not randomly given in the points or in the noise is fixed or if is a deterministic error, this one you can have a more deterministic kind of estimate. Okay. Okay, I think they still have something, and we have all kind of other situation we discussed. I think I omit all these. This is a reference. I think many of them are already available. And thank you.